Hey, Pradeep, can you hear me?
I can hear you.
Yes, Chris.
Okay, good. I'm going to mute myself again.
I can hear you.
Yes, Chris. Okay, good evening, good afternoon, good morning, and welcome to day 4 of the workshop on AI and HPC technology in semiconductor manufacturing in collaboration with IIT Madras. I am Pradeep Ramachandran from KLA, one of the organizers of the workshop, along with Rupesh Nasre of IIT Madras, the Nodal Center for Training in AI and HPC under the National Supercomputing Mission. A brief relook at the agenda, like we've been doing over the last few days. So this workshop is laid out as a sequence where we started on Monday with Chris talking about modern AI in manufacturing, what the challenges are and what the problem space definition was. Jacob then went ahead to talk more about details of specific challenges and what happens when one tries to adopt machine learning into manufacturing. Steve had a wonderful overview yesterday about the infrastructure challenges in building AI models in the fab, where he actually told us what it takes to build a full-scale AI model inside an airtight environment like a fab itself. Mark will be going ahead today with talking about more details about the hardware, focusing a little more on minimizing copy overheads inside the GPU. And I'll go last tomorrow talking about AI inference on CPU. So the first 3 talks that were completed on Monday, Tuesday, and Wednesday, respectively, the slides are already available on the workshop website and recordings are available on YouTube. You can get to the recording from the NSM webpage itself. Today's talk from Mark will focus on minimizing copy overheads while sharing GPUs in a box. Before we go there, I would like to have one clarification about the intended audience or the assumed audience that we had when we actually prepared these talks. Now, of course, everybody is welcome to attend these talks. We are glad that you're here to listen to us. But when we prepared the talk, our idea of an ideal audience was someone who was either a senior, that's the 4th year, in engineering, or first year MS student, either in computer science, electrical engineering, or in the sciences. For those who are less experienced, we of course recommend that you attend this talk, but you also additionally grab some more fundamentals around machine learning algorithms, distributed computing, semiconductor device modeling, GPU programming, and then come back and see this talk again, which will be available on YouTube. That way, you not only will get a better understanding of the space, but you'll also appreciate some of the nuances that we're discussing over here. Finally, we realize that we're using a lot of terminology here, which, for us who are deep in this, it becomes very obvious, but for somebody who's listening to it for the first time, it might not be. So we actually are trying to make sure that we clarify the terminology used in every talk as we proceed. Now, before we start the talk, there are a couple of workshop logistics that I would like to reiterate. Firstly, I'm glad to see over 1,500 participants again on Zoom and several joining live on YouTube. It's the same Zoom link to join every day's webinar. The YouTube live stream is per session. Preferably join over Zoom because you get full access to Q&A experience over there. Of course, you can also view live on YouTube as a backup. Each session has been following a similar pattern and we'll continue that. The first 10 minutes, we'll go over basic setup, introduction, some logistics as I'm doing right now. The next up to 40 minutes will be the talk itself. Now, given the scale of the workshop, we decided to pre-record the talk to avoid any connectivity issues. And we will make sure that we reserve at least 10 minutes for Q&A. Now, I should highlight that the last couple of days, the kind of questions we've been getting are amazing. It's been really good. Been very happy to answer those questions, so keep them coming. Feel free to post your questions at any time in the attendee Q&A window. As we have the speaker and the panelists available throughout the session, we will try to answer some of the questions via typed answers during the talk, and we'll select a few and the speaker will answer them live at the end of the talk. If you're interested in a certificate of participation, please make sure to attend at least 80% of all 5 talks. Today is day 4. Attendance, if you're on Zoom, is automatic. It's automatic, nothing to fill. Just make sure that you're joining with the same name and email address as what you had used to register the webinar. On YouTube, I will post a link to a Google form in a pinned comment. Please make sure that you fill that out with your name and your email address. In case your name and email address on Zoom don't match what you have registered with, just join the YouTube stream. I've put a link already in the chat. Join the YouTube stream and fill that form out. Again, remember, if it matches, there's no need for you to join and fill the Google form out. You can just leave it on Zoom and attendance is taken care of. Now, based on the experience, especially the first couple of days, we decided to do a little bit of detail of housekeeping such that both the Zoom and the YouTube channels are clean and relevant. The important thing that we want to highlight is please exercise your judgment in Zoom Q&A and in the YouTube comments, right? Please avoid posting greetings in channel. Remember, we are having in regularly over 3,000 live attendees across all days. So, live, a lot of highs end up filling the channel, but please don't do that. If you're interested in opportunities with KLA, we are very interested to talk to you. Please reach out separately. Don't post it in Q&A. It's not the way to reach us. If you have audio video issues, please check your volume or move between Zoom and YouTube, whichever the one works for you, please attend over there. Because from our side, we have really taken great pains to make sure that the audio and the video quality is very high end, and it's up to Zoom and YouTube to deliver it to you at high quality, right? So please bear with us and try to check your volume or move between streams if it doesn't work for you. Again, to reiterate this question of attendance, because we keep seeing this question coming up, workshop attendance is automated via Zoom. On YouTube, please fill out the Google form. No need to do both, right? And don't post your email address or Q&A, email address in the question answers or comments. We don't do attendance that way. And again, to reiterate, please reserve Q&A and comments for relevant questions for speakers and panelists. We are here, we are listening, we are trying to answer as much as possible. If we keep the noise low, you'll actually get very good signal from the speakers who will be able to share very good answers to your questions. That said, I hope you're ready to raise a head and listen to Mark speak about how to, oops, sorry, I forgot to update the title here. The title of the talk today is not building AI models in the fab. It is minimizing copying overheads when sharing GPUs in a single box. I apologize for that. A quick introduction about Mark. It's really a pleasure to have Mark over here. Mark has been building software infrastructure tools and frameworks for over 20 years. Recently, his focus has been on supporting KLA's HPC and deep learning efforts with the goal of integrating GPU and deep learning algorithms with existing legacy vectorized CPU algorithms. That introduction down, let's roll the video and listen to what Mark has to say about sharing GPUs on a single box.
And finally, I will put all the pieces together.
I apologize. I just realized that audio was not going through. So I'm going to re-roll the video from the top.
Good evening, everybody. Welcome to tonight's talk, where I will be discussing minimizing copy overhead while sharing GPUs within a single box. The presentation is going to be broken into 5 pieces. The first bit is I'm going to talk about the assumed background in the audience. After that, I'm going to dive into the nature of the problem that we are trying to solve. I'm going to take a short period of time to talk about the design philosophy that went into the solution. I'll then cover the technologies behind the solution. This is going to be the bulk of the talk. And then finally, I will put all the pieces together and show what we wound up doing. So, assume background. Unlike most of the talks up till now, there's no semiconductor knowledge required for this particular talk. The problem and the library solving it are quite low level, quite general, and we built it because we needed it, but it is not semiconductor industry specific. So for those of you that have been a little bit overwhelmed with things like defects of interest and broadband plasma, hooray, this talk will not be doing that. It will, however, be focusing a lot on computer programming. So there is assumption that you have programmed computers before. C, C++, Java, Python, doesn't matter too much which, but this is a programming talk. There's also going to be some discussions about internal operating systems. So in this particular talk, specifically on Linux, again, as with all of these talks, everybody is welcome to stay and listen. So if you think you might get something out of it, please stay around or at least try it out. But this is a talk about programming problems and a solution. So, our problem. Our typical compute nodes, so an individual computer box, has 32 or more CPU cores, and on that we're running 32 or more CPU processes. Each of these processes wants access to a GPU to run deep learning loads. Deep learning loads are what run in sessions, and a single deep learning session can only be used by one process. So if we've got 32 CPU processes, naively we would need 32 deep learning sessions. And the problem is we do not get very many sessions per GPU. Deep learning sessions require a lot of GPU memory, and you may get 2 or 3 sessions per GPU. So if I've got 32 or more CPU processes that want to run on GPUs, and I can only do 2 or 3 sessions per GPU, we have a problem. Because if I ship 4 GPUs in a box, I've got between 8 and 12 sessions that I can run. I'm going to want to run at least 32. This just does not work. There are standard techniques for solving this. There are sharing technologies that set up processes in the middle, and everybody uses network copying and marshalling to get to the middle process, which will then hand things out. The catch with that is it works, but you take a substantial performance hit because of the copying and the data marshalling, and we do not want to do that. That means we would need to ship more boxes to get done what we want done, and that costs money. So the trick is, how do I get 32 CPU processes to share maybe 8 TensorFlow sessions running deep learning loads without blowing performance and without basically taking an easy way out. Understand, all of our problems here go away if we're willing to run slower and throw money at the problem. The engineering challenge is we want to run quickly without spending the money. So before we dive into what we're going to do, I want to talk a little bit about a design philosophy. So the easiest thing to do is to understand exactly the problem you're trying to solve on a given time, and you build a solution to solve exactly that. It's fairly easy to do, you know when you're done. The problem is this isn't very good, because if your problem changes, and it often will, you're going to have to come back in a year and solve the problem all over again with a slight variation. So if you don't want to be in a constant loop of last year's solutions don't work, you're going to have to do a little bit more than just solve today's problems. The next thing you can do is look at your problem today, fully generalize it so that you can solve any possible variation of it and build a highly complicated, fully generalized solution. This is equally bad for a different reason. The chances that you're going to need most of what you build are low, so there will be an enormous amount of wasted effort and time, and you're going to spend a lot more time debugging the complexity that you will not get any benefit from. If you're Facebook or Google and you may need to do this, fine, perhaps. Very few of you will be in that situation. So mistake number one is only solve today's problem. Mistake number two is solve every possible variation of the problem you could imagine up front. One means you're going to have to come back in a year. The other means you're going to spend an enormous amount of time on stuff that does not matter for you ever. The next step is to try to split the difference a little bit and come up with a simple generalization that's larger than today's problem, is something you could easily imagine needing in a year or two based on your knowledge of the problem space, but without getting into the deep complexity. So basically, you're splitting the difference. Do the easy generalizations and skip the hard ones. And then the last one is you might have the simple generalization in mind, but you don't necessarily need to implement all of that implementation on day one. So a very reasonable place to land is understand today's problem, design a generalization that doesn't require a lot of complexity, build that part of the generalization you need, and maybe a little bit more if it's easy, and then stop there. In the future, people can implement up to the simple generalization, and with a little bit of luck, you don't have to do the super complex thing ever. If you do, you'll address it when you need it. So that's today's design philosophy. So I'm going to describe today's problem. I've already done that. We've got a bunch of software processes that need to share some resources, GPUs, but I'm not going to solve every possible variation of that across boxes over a network. We're doing this within a box, and we're mostly doing this for GPUs. So we're going to have a simple generalization to this that can solve slightly more than we need today, but there will be a lot of things that we can't solve. All right, diving into the technologies behind it. The first thing we need to understand is how Linux processes work. So a Linux process, very broadly, comes with three pieces. There's code. This is the actual instructions for the CPU. There's constant data, and then there's the rest of the data that can be modified and manipulated. Stack data goes here, heap data goes here. And every Linux process has a process ID, which helps you keep them separate. So in this example, we've got a single Linux process represented, and it's got a process ID of 100. The way Linux makes new processes is something called forking. So it takes the base process, forks it, and basically makes a complete clone of the original process. So the data is the same, the constant values are the same, the code's the same. The process ID is different, and a few other small nitty things are also different. But all of the data in these two are identical, which means you can't really tell the difference between them. And in fact, you could swap them and everything would be fine. So Linux starts launching a new process by making a copy of the one it's currently running. Does this very efficiently. It's not going to run as slowly as you might think, but it definitely starts by making a copy. The general next step is to call something that Linux has as an exec, short for execute. At that point, you replace the code, the constants, and the data with your copy, with the code, constants, and data with the new process that you actually want to run. So you keep the process ID. We were 100 and 101 after the fork. We're still at 100 and 101. But now the data between these two is completely different. The constants are different, and the code is different. So these two processes can now go off on their own and do their own thing. There's one very important exception on the copying and the cloning. If you do a fork and the original process has something called private shared memory, after the fork, the shared memory is going to be copied just like the data, the constants, and the code, except the shared memory is actually shared. any changes in one bit of this will be resulted in the other. So basically, there's only one copy of the shared memory, even though there's two completely separate processes. After the fork, if I change the data in one of the processes, the other one will not pick it up. They start off the same, but they're not going to stay that way. The exception is in the private shared memory, where changes made by one of these processes will affect the data that's seen by all of them. So that's the first trick. We're going to use fork and we're going to use private shared memory. Private shared memory can also be closed. So I could make a copy of the process. I've got process IDs 100 and 101 by forking, and then process ID number 101 can close the shared memory. So we had it, it was common, now it's not common anymore. Process 100 is the only one that has it after that. And if I stamp this out as a bunch of copies, we can imagine the following. I've got my base process 100, and I'm going to fork and make process IDs 101 and 102. 101 and 102 are going to close all but one of the shared memory blocks. And then we've got this other guy over on the side, 500, who's going to keep everything open. So the upshot now is 101 can make changes to the shared memory that it sees, and processes 100 and 500 will see those changes. But process 102 won't, because process 102 can no longer see the shared memory for 101. 102 does exactly the same thing. It's got its shared memory. Everybody can see it except not process 101. So for processes 101 and 102, they've got data that they can change, and some other folks can too, but they're isolated from each other. If we then take this technique and make a large number of copies of processes with forks, say 101 through 132, I can wind up with a situation where I've got 32 processes, each having one and only one shared memory block. And then I've got off to the side processes, say 500 through 504, that can see all of the shared memory from all of the processes 101 through 132. So for terminology's sake, we're going to call the processes over on the right child processes, and we're going to call the processes over on the left helper processes. And the trick here is only the processes over on the left, processes 500 through 504, in the example, will have access to a GPU. And each of these processes will have access to one session. So I've got my 32 processes over on the right that want to get access to the GPUs. None of them have direct access. I've got my processes over on the left, each of which has access to one GPU session. And the processes over on the left, the helpers, can actually see the shared memory data from any of the processes over on the right, the children. So the trick then becomes getting control transferred from the children over to the helpers. We're going to do that with a message. A child process can send a message to the parent, not directly to the helper. The parent can then dispatch that message to any available helper. The messages will get queued up if there's no helper available. And the messages are very, very simple. They're a function pointer, some code that you wish to run over in the helper, and they are data which are parameters, and the parameters can be anything you like. The only important bit is that the parameter data has to be in the shared memory of the child. So if we go back, the children have got data that's private to them, and they have data that's shared. The data that you want to be used on the GPU has to be in the shared memory block, but that's the only constraint. We then basically have two messages. Send a message and read a message. And messages go in pairs. So you'll send a message, which is do something, and then you wait for the response with read a message. An example function might look like this. It's got a function name, it's got a single parameter, which is a pointer to a bunch of data, and that's it. You're not allowed a return type. You put the return type in the passed-in data, and obviously the caller and the function have to agree on how the data is going to be organized. But beyond that, there are no restrictions. So in this case, we're just printing out a little message saying, hi, I'm the helper, and I'm getting some data. Okay. Our messages are small. The 2 pieces of data that we need to send back are only 16 bytes. The infrastructure that we built adds some overhead, and they pad out to 64. But 64 bytes fits within a cache line and is basically no more expensive than 16 bytes. Messages are sent only within a single OS domain. So I can send a message to any helper process running on the same computer that the child process is, but I can't send them between boxes. There's no network traffic here. We're using POSIX pipes to send messages. Pipes basically just move data from one end to another, and they maintain order. So reads and writes, very simple, provided by most operating systems, maybe all. And the parent process is responsible for the message dispatching, but the message dispatching is quite simple. It's simply a loop. There's no threading, there's no contention, there's no locking. There's a single loop that just goes around looking for messages that need to be sent from child to helper or helper to child. And because the single loop knows whether helpers are busy, we can actually skip reading for messages to be sent until we know there's a landing spot. So this is very simple. It's a loop that only looks for stuff to send if there's a place to put it. When there's a place to put it, it waits until something shows up. Benchmarking this on my laptop computer, I'm seeing about 150,000 round-trip messages a second, which is more than sufficient for what we need. Our inference graphs generally run between 4 and 20 milliseconds, so this is plenty of time. So that's the pieces. We use fork, we use private shared memory, and we use messages to send stuff back and forth. The shared memory is awkward. If you have 100 megabytes of shared memory and a single pointer to it, that's going to be tough to manage. We stacked a malloc and free package on top of this, so they look exactly like normal heap memory in a C program. The malloc and free were trivial. We basically found something on the internet, about 150 lines of code. It's not super sophisticated and it's not super fast, but we don't need it to be. So this is an example where we could complicate things by implementing a much more sophisticated, much more performant malloc and free. But until there's some reason to believe that we need the performance, there's really not much reason to go from 150 lines of code to 10,000 with all of the necessary debugging. So if we put this all together, the sequence is this. Somebody who knows what's going on needs to launch the parent process, because that's what's going to get everything started. The parent's going to set up the shared memory regions, 1 per child. The parent sets up pipes to each child process and to each helper processes. And we do this with a single API call. Launch, we give it a count of children, an array of parameters for the main methods for those children, the block sizes that for the shared memory we want to share, and the number of helpers to launch. The parent forks the helpers as part of the launch. The parent forks the children as part of the launch, closes the shared memory regions that are not supposed to be used in each child, and at that point the children have 4 APIs that they need to use. Shared memory, malloc, and free, and shared memory send message and receive message. And the code is exactly what they would have normally done, except to run on the GPU, you send a message rather than calling the function directly. And that's it. 1,500 lines of code, no copying, no marshalling. The data that you want is exactly the data you've got. And the message dispatch latency is low, and the throughput is high. So let's talk about some of the design decisions that went into this. There was nothing in the original specification that said we needed helper processes. The parent process could, in fact, be the one that talks to the GPUs. And the logical question then is, why are we launching helper processes? It complicates things. We've got to send a message to process. You bounce everything through the parent. Why are we doing that? And the answer is there's no guarantee that the code is going to not crash. If the parent goes down, everything fails because there's nowhere to dispatch. There would be no one to talk to the GPUs. So this is an example where we didn't just solve today's problem, which is share the GPUs. We decided to extend it a little bit and say, and we want some robustness. If a helper goes down, the parent stays up, all of the children stay up, and all of the other helpers stay up, and the parent can relaunch the crashed helper, which means that the processing is slowed down, but it's not stopped. So the decision was, we are fast enough on our dispatching, and the reliability is important to us, that we want to increase the reliability of the system in exchange for a slightly more complicated design than is strictly necessary, in exchange for a slightly lower message dispatch rate, because we're already plenty fast enough. All right, we can clearly dispatch messages faster in the parent if we have multiple threads working on it. So why do we have a single dispatch thread in the parent just doing a loop? And the answer is, we're fast enough, and multi-threading requires a lot of locking, which tends to be error-prone. So this is an example of a case where we know how to build a system that's got higher performance for this one small corner, but there's absolutely no reason to believe right now that that performance would show up in anything we care about, and it would make for a more complex system which would require more debugging. So without any reason to believe we need the performance, we're going to stay with a simpler design. Notice that the children can't tell the difference. So if we decide we need the performance in the future, we can actually modify the parent's dispatcher to be faster, and none of the child code's going to have to change. But we're going to choose not to make that decision, not to do that work until we've got some reason to think that it's important. All right, our malloc and free for the shared memory only works in the child. We don't allow the helper processes to do that. And the question would be why? And the short answer is because they don't need to. Maintaining consistency on a shared memory heap across multiple processes is much more challenging if many processes can allocate at the same time. You've got lots of parallel contention to worry about. So as with the single dispatch choice in the parent, this is a case where we chose to keep things simpler than they could be. We're willing to trade off a little bit of capability here because we don't think we need that capability. Again, if we need it, we can obviously extend the system to allow allocation from multiple processes, but right now that seems like a bad choice. The dispatching right now does not see any difference between any of the helper processes. Any message can get sent to any available helper process. Right now we're doing it that way because that's all we need. You could easily imagine a situation where you've got two different GPUs running different deep learning algorithms, and where the thing got dispatched mattered. Again, the design is easily extendable to that. You could add an extra parameter in the message, which would provide routing information. And we may wind up doing that in the future. But again, until we've got some reason to believe we need it, doing the coding up front and adding the complexity seems like a poor choice. So the architecture and the design allows it. The implementation here, however, does not do it. We will provide that implementation later if we need it. Now we've got two constraints to think about. The first one is this approach simply doesn't work on Windows. Windows does not work on a fork exec model. So if you need this capability on a Windows box, you're going to have to do something else. And I have no idea what that would be. I don't understand Windows nearly as well as I do Linux. The good news is for us, all of the loads that we care about that are doing deep learning are running on Linux. So this is a constraint on the design and the architecture and the approach, but it seems like a fairly small one. We do not currently have a requirement to run on Windows. If we do, somebody's going to have to revisit this. And the last constraint is right now we're only allowing one message to be outstanding at a time per child. The idea here is we are expecting the number of children to seriously outnumber the number of processes using the GPUs and running deep learning. So having one child having not just one message outstanding, but two or three, probably means the other children are really backed up. If we ever get to a situation where it's extremely common to want children to have multiple messages outstanding, we'll have to revisit. And again, we'll have to change the message data and add some queuing capability. This would probably be done in the parent. So again, we don't have to change anything, but we're not going to suffer the performance hit, the complexity hit, the engineering hit, and the debugging hit solving a problem that we do not think we've got today. The architecture and design can be extended to it, so we haven't boxed ourselves into a corner, but we're not going to do the work until we've got some reason to believe that we need it. So there you have it. A little bit of low-level trickery with Linux forking, private shared memories, and piping, and we can have a large number of CPU processes sharing a small number of GPUs running deep learning loads and keep the performance high and the overhead low, because the overhead is just transferring control. No data copying, no data marshaling. Thanks for coming here, and we'll see if we have some time for a few more questions. Thanks.
All right. Thank you very much, Mark. That was really a very nice level of detail for talking about GPUs and shared memory over there. So we got a lot of very good questions in the Q&A that Mark and team have actually answered quite a bit of them already. But we've selected a few to actually, several of these have actually been answered already, but I thought it will be good to repeat them in live Q&A so that those who have not gone and seen the answers are able to get a gist of what the answers were. So Mark, let me lead with the first question. What is data marshalling?
Yeah, so let's back up. You can hear me?
Yeah.
Good, okay. So imagine you've got an in-memory data structure in some process. It could be anything. It could be an array, it could be an integer, it could be a complicated linked list or a map. It could be a graph with lots of pointers going every which way. If I need to get that data structure to another location, maybe I want to store it to disk, maybe I want to send it to another box, maybe I want to get it from one process in a single box to another one. A fairly common technique is to basically turn the in-memory data structure into an array of bytes. And then you pretty much will have an array of bytes. I can copy it to a disk, I can send it over a network connection, and then on the other end, you take the array of bytes and you reassemble it into the in-memory data structure that you had in the first place. Perfectly general solution. People have been doing this for decades. The catch is marshaling is expensive compared to not marshaling. So the reason we're trying to avoid this is it works, it's known technology, there is no technological problem with it where it won't get the job done. The catch is it costs a lot of CPU cycles, and we'd rather use those CPU cycles for running our algorithms rather than moving data. So marshaling is basically a way to turn in-memory data structures into an array of bytes. Unmarshaling is a way to turn an array of bytes back into an in-memory data structure.
Okay, excellent, thanks. Next question, I saw quite a bit of these come up, right? Can you re-clarify the difference between fork and exec?
Yeah,
so,
fair enough, we'll try this again. So imagine I've got some program running in Linux, or any Unix, but Linux is the one everybody's running these days. So fork basically says, make a complete copy of the process that I'm running. So imagine you're running Microsoft Word, which is a bad example because that's a Windows product, doesn't run on Linux. You'd then have two copies of Word running. They'd have exactly the same data loaded into memory, which means they'd have exactly the same document. The page that you were viewing would be exactly the same page, exactly the same scroll location. Everything would be the same. The trick is you start off as copies, but you're not going to stay there. They are independent. So going forward, if you start editing the document in one of your words, it's going to be different. The other version of Word will not pick those changes up. So fork is basically make a clone of the current process, but they're independent. So if you make changes to one, it won't be picked up in the other. Exec is replace the current process with a brand new one. So for example, maybe I was running Word and I exec, and now the Word has been completely thrown out and I've replaced it with Excel. So fork is a clone operation. Exec is replace my clone, just rip out all the guts and drop a brand new program in, usually from files loaded on a disk. So the trick here is we're doing the first half and then stopping there. It's totally legal. It's just very unusual. So we're counting on the fact that Linux does it in two parts. Windows does not. Windows pretty much just has an exec, except that's not the name of the API. So they don't have a way to freeze it halfway through. Like they may have another way to do this. I just don't know what it is. But that's what fork is. Make a clone of me, start off the same, will diverge over time as changes happen.
Okay, great, thanks. It's a pretty neat trick, I should say. Next question: what is an API?
API is short for Application Programming Interface. Generally speaking, it's the set of functions that you provide to operate on your library, your program, whatever. So in our case, the API, the Application Programming Interface, has the launch function. It's got send message and receive message. It's got the shared memory malloc and the shared memory free. And the reason that the APIs are important is as long as the API continues to work the way you defined it to, you can change the implementation and the clients don't have to change. So imagine I've written some program that makes use of this library with the shared memory trick. So we've launched a bunch of things with launch command. We've got a bunch of shim malloc and shim free calls. We've got a bunch of send and receive message calls. And we decide we need to change it so that the malloc and free that we're providing are faster. Right? If you remember, I talked about the fact that we're shipping with a very simple one because honestly, we don't need something more complicated. Well, let's assume things change. I need the performance to be higher. As long as everybody's just using the malloc and free API, I can replace that implementation with a much faster one. It may be a lot more complicated, it may require a lot more debugging, but it'll be faster. And all the client code has to do is relink, and they continue to run just the way they were. It's just that now their mallocs and frees run faster. If it turns out that I want to speed up the message dispatch and move away from the single thread to maybe a multi-threaded dispatcher in the parent with locking and queues and stuff like that, again, I can do that, and the client code, the code written against the library doesn't have to change as long as the send and receive messages don't change. So it's a way to shield implementation details, often involving trade-offs and complexity, resource management, and speed from the client code who just wants to get their work done. So API, Application Programming Interface.
Okay.
They're a good thing. You want them.
Fantastic. Yeah, of course, it's a key component of any library that you integrate into a system.
Well, it's a key component of writing code. Imagine I'm building a large system. I benefit from breaking the system up into libraries, even if I'm never going to ship them to anybody else. I might build something as a library with exactly one user, which is me. The API helps prevent the rest of the system from getting tangled with the internal details of this piece of the system. So libraries aren't just for other people. Libraries are an excellent way for you to organize your own projects, your own data, even if you're not planning on reusing the library or letting anybody else use it. The APIs are a way to keep your sanity and keep your code from turning into a spaghetti mess.
All right, great, thanks. So the next question, I don't know if the person who asked the question was complaining about the naming or had a genuine question, but I'll still replay it.
Okay.
How can a memory that is shared between multiple processes be private and shared at the same time? The words private shared memory.
Right. So first thing is, I didn't pick the names. I am using the names that the Linux community and the Unix community in general have settled on. So please don't blame me for English spelling, and please do not blame me for private shared memory. The private is, there are other shared memories that are given names and you can find in a file system. And what that means is any process, not just one you fork, any process, if it knows the name, can map the shared memory into its own address space. So you could have two completely separate programs, two completely separate code bases. If they know the name of the shared memory, they can both use it. Now, the difference is the data will be shared, but the memory locations will be different, which means you can't pass pointers back and forth, which means you can't pass, if you put a graph in there, one program can use it, but the other won't because the pointers will be invalid. The data will all be there, but the pointers will be garbage. Private shared memory is shared memory, but it doesn't show up in a register anywhere. If you're not part of this parent-child fork thing, there's no way for you to find the shared memory and there's no way to hook it up. So it's private in the sense of it has no name and there's no way for anybody to hook into it if they're not already part of the group that's playing nice. Others you can connect to via a name.
Okay.
So anonymous would probably be a better choice for it than private.
Yeah.
Right, anonymous, I have no name. But as I said, I'm not in charge of naming these concepts. The Unix and Linux community got to it 30 years back, and we're just going to use their names.
All right, great, thanks. So continuing with the Unix and the Linux community, can you clarify a little bit about how POSIX pipes work?
Yeah, so pipes are basically a way to send arrays of bytes from one process to another running under a single operating system. So you can basically think of it like a socket where you've got two ends, that's it. One guy pushes data in, the other guy can pull data out, but it only works within a single box. So I can use socket communication to go box to box, which is basically how the internet works. Pipes don't do that. If I need to talk from one box to another, even if I have a cable in the middle, pipes won't work. I've got to use sockets. The reason to use pipes, and the reason to use pipes here, is pretty much the same reason that we use the private shared memory, which is really anonymous but not private. I can set up pipes that are only visible by the parent-child, parent-helper pairs. So the outside world can't see the communication mechanism. They can't hook into it. They can't interfere with it. So pipes are more restrictive than sockets, but I don't need the capability of the sockets. And they have the advantage that I can hide them in a way that you can't hide sockets. In this case, they also tend to run faster, which was a nice plus. But the big win was really just I don't need the capability of the sockets, and I really don't like to advertise the pipes to the outside world. So, but basically pipes, you put bytes in one end, somebody else takes them out the other. They maintain their order. The ones that go in first come out first. That's it, no trick.
Fantastic, thanks. Yeah, and I saw a lot of people asking this question. I really encourage you to go and read up about pipes in any OS textbooks. Lots.
Yeah, I mean, fundamentally, this is sort of if you're a computer sciencey person, you have to take an operating systems class. So when you do, pay attention. Pro tip.
Okay. And so the last question, not really a question, but more a comment from me, Mark, right? If you can reiterate how the concept that you described today links back to the AI world that we've been talking about.
Yeah, so the linkage is we need this. As I said, we've got, maybe in a box, we'll have 4 GPUs, somewhere between 1 and 8. Let's pick 4 because that's kind of in the middle. I can maybe get a total of between 8 and 12 TensorFlow sessions on there. And I want all 32 plus of my processes to be able to run inference using those TensorFlow sessions. So I've got to have some mechanism to share them. Otherwise, I'm only going to be allowed to have 12 of my legacy processes. And I need the 32 because that's what I need to get the legacy load run. So this is fundamentally not anything to do with deep learning or AI, except we need this to efficiently use the hardware that we want to use to run our deep learning and AI loads. The library doesn't know anything about GPUs and it doesn't know anything about TensorFlow. So you could use this with PyTorch if you wanted to use a different framework. You could use this with some non-GPU accelerator, right? There's like 500 small companies building them now, all of them getting ridiculous amounts of venture capital money, most of whom will be dead in a year. But there's going to be a few that are going to work. And I suspect they're going to have exactly the same problem. You can't run as many sessions on them as you want, and the sessions natively don't share. So again, planning a little bit for the future, we had no reason to build this around GPUs only, so we left all the GPU specific stuff out. The guys using the library can put that in if they want to. But fundamentally, it comes down to, we need more people using the GPUs than we're natively allowed. We need a trick, and this is the trick.
Okay, great. I think that pretty much sums it up from the question and answers that I can see. Just to reiterate, there are a bunch of quick Q&A that have already been answered. Please go ahead and review them if you've asked a question, or if you had a question that was asked by someone else, it's already been answered in the Q&A, please review them. Thank you again, Mark, for spending your time putting the talk together and all the question and answers. So I think with that, we'll wrap up today. We come back tomorrow talking about AI inference on the CPU, which will be the last talk of this workshop. So I'll see you again, 8:30 p.m. India time, 8 a.m. Pacific time, Friday. Until then, you got back 10 minutes of today. Thank you very much.